Hi, everybody. It's Professor Mitchell, and today we're talking about section 8.2, integration by parts. So this is technically your second integration trick after substitution. I don't count the formulas as integration tricks, really. I do want to explain briefly where this comes from. So this is kind of the backwards version of the product rule. So if I write the product rule in its differential form, hopefully you remember a little bit about differential form from Calc 1. The differential of uv is equal to u times the differential of v plus v times the differential of u. So what I'm now going to do with that equation is integrate both sides, which gives me this. And then the integral of the differential of uv is just uv. And now if I solve that equation for integral u dv, you get this. The integral of u dv is equal to u times v minus the integral of v du. So the way that you use this, normally you use it on the product of two functions. You designate one part of the integrand to be u and the other part to be dv. The catch is that dv needs to be something that you already know how to integrate. And ideally, u should be something that gets simpler when you differentiate it. All right, so let's do some examples. Here are the first round of examples. Whoops, I didn't mean to do that. Let's go over to the tablet, and I'll show you how this works. All right, so the first example is integral theta times cosine pi theta d theta. So the way I like to write integration by parts is to say let u equal, and then let dv equal. I like to write the word let because it emphasizes that you get to choose this part. All right, so my choices are, I could make u equal theta, or I could make u equal cosine pi theta. I am going to go with the first option, and I'll tell you why. It's because theta gets simpler when I differentiate it. If I were to integrate theta d theta, it would turn into theta squared over 2, and that would make my new integral even worse. Okay. So now, if u is theta and dv is cosine pi theta d theta, then that means that du is just d theta. Notice I'm not writing let because you don't get to pick this part. And then v is the integral of cosine pi theta d theta. Now remember in the last section, I mentioned what I call baby u substitution. This would be another good example of baby u substitution. The integral of cosine pi theta is sine pi theta, but then you have to put a 1 over pi out front, basically to make up for the chain rule. So what I want to emphasize to you is that what's happening over here is differentiation, and what's happening here is integration. Okay. So now remember our integration by parts formula. It said that integral u dv is equal to uv minus integral v du. So in this problem, that translates into integral theta cosine pi theta d theta is equal to u times v, which is going to be 1 over pi times theta sine pi theta minus integral v du. So here is v, here is du. So in this problem, that's going to turn into minus 1 over pi. I might as well write that in front of the integral, times the integral of sine pi theta d theta. So the whole point of integration by parts is that it creates a new integral that you know how to solve, or that is at least simpler than the one you were given. All right, and in fact, I do know how to integrate sine pi theta d theta. That's going to be another baby u substitution. So I think we're just about ready to write our answer. We'll carry along this first term, 1 over pi theta sine pi theta. And then a couple things to note. When you integrate, the integral of sine is negative cosine. So that's going to turn this minus back to plus. And then by baby u substitution, another 1 over pi is going to pop out. And so this is now going to be 1 over pi squared. And it's going to be cosine pi theta plus c. And that's it. That's integration by parts. All right, next example. Whoops. There we go. So the next example is a definite integral, the integral from 1 to e of x cubed natural log x dx. So now let's figure out what is u and what is dv. Okay, so remember the number one most important thing, dv has to be something that you know how to integrate. And believe it or not, we have never talked about how to integrate natural log of x. We've talked about how to differentiate it, but we've never talked about how to integrate it. And there's a really good reason for that, which I will share with you in just a few minutes, maybe after we do the next example. So I have no choice but to make dv x cubed dx. Now, unfortunately, that is going to get a little more complicated when I integrate it, but the good news is that natural log x, well, something really good is going to happen with that. So then du, again, we know how to differentiate natural log of x. That's just 1 over x dx. And the integral of x cubed dx by the backwards power rule is x to the 4th over 4. So by integration by parts formula, integral u dv is equal to uv minus integral v du. Okay, so we have the integral from 1 to e x cubed natural log x dx. Now, when you're doing a definite integral by parts, what you have to remember is that the uv part, so in this case, x to the 4th natural log x over 4, so that is part of the antiderivative. So we are eventually going to plug in e and then plug in 1. Okay. But then we have to also do the integral from 1 to e of v du. And now look at the cool thing that happens. V du is x to the 4th over 4 times 1 over x. So that's just going to be x to the 3rd over 4. And I'm going to write that as 1/4 x to the 3rd dx. All right, so, well, why don't we go ahead and plug in e, plug in 1 into the first part of that. So that's going to be e to the 4th natural log e over 4 minus 1 to the 4th natural log 1 over 4. And then the integral of x to the third is still x to the fourth over 4. So this part here is going to be x to the fourth over 16. Because remember, there is a 1/4 outside. So 1/4 times 1/4. Plug in e, plug in 1. All right, so natural log e is equal to 1. So this is just e to the fourth over 4. Natural log 1 is equal to 0, so we can ignore this term. And then, be careful with that minus sitting outside. This is going to be e to the fourth over 16 minus 1/16. All right, so I'll pretty up this answer as much as I can. We're going to need a common denominator 16. To get that, I'm going to do this by 4 over 4. So we have 4e to the fourth over 16 minus e to the fourth over 16 is going to give me 3e to the fourth over 16. And then we have minus 1/16, so we can just make this plus 1. Notice that is a perfectly good real number. It looks like an algebra problem, but it is the value of that definite integral. All right, and then the last example in this batch might look a little funny. It's just the integral of inverse sine y dy. So it turns out that integration by parts is useful for integrating certain just single functions. And the inverse trig functions are an example of that. And by the way, so is natural log x. Remember a few minutes ago, I said we didn't know the integral of natural log x. It turns out that you find the integral of natural log x by using integration by parts. Okay. So I think I'll leave that one for you to try. It works very similar to how this one's going to go. So we're going to let u equal inverse sine y. And we're going to let dv be just dy. And now maybe this is worth saying again. Remember, when you go down on this side, you're differentiating. When you go down on this side, you are integrating. All right, now what is the derivative of inverse sine y? I know you have that one memorized. And if you don't have it memorized, hopefully you have it written on a piece of paper somewhere within reach. The integral of inverse sine y is 1 over the square root of 1 minus y squared dy. And of course, the integral of dy is just y. All right. So integration by parts formula says integral u v. I'm sorry. Let's try that again. Integral u dv is equal to uv minus integral v du. So in this case, the integral of inverse sine y dy is equal to uv, which is y inverse sine y, minus integral v du, which is the integral of y over the square root of 1 minus y squared. All right, so look at that integral for just a few seconds. You know, at a first glance, it looks kind of terrible. Is that an integral that you know how to solve? Well, yeah, I think it is. Believe it or not, that is a Calc 1 integral. That is just a regular old substitution. So now I'm finished using u the way that I used it in the integration by parts. So I suppose I could make this a u substitution. If I make u 1 minus y squared, that would make du negative 2y dy. And I actually do want the minus sign, right? I have a minus sign here. I just don't want the 2. So why don't we say 1/2 du is equal to negative y dy. And then what's going to happen, I guess it's okay to get rid of this stuff up here. We are going to have the integral of inverse sine y dy is y inverse sine y. And now minus y dy is going to get replaced with plus 1/2 du. And so this new integral is going to be du over the square root of u. And why is that a Calc 1 integral? It's because you want to think of that over square root of u as u to the negative 1/2. And then use the backwards power rule. All right, so how does the backwards power rule go? You add 1 to the exponent and divide by the new exponent. Normally, I would just say that's 2 times u to the 1/2. And I could have said that, but I figured I'd write it like this. And then you can just get rid of those 1/2s. Oh, wait, hold on. We just did the integral. Okay, so I will put a plus c there. And now I'm ready to write the final answer because, as always, it's not about you. In this case, it's about y. All right, so final answer. Y inverse sine y plus u to the 1/2, which I'm going to write as the square root of 1 minus y squared. And don't forget the plus c. All right, so I'm not a big fan of gimmicks, but this one seems pretty harmless. This is called Lipit. And this is a trick for choosing which part of the integrand to make u and, well, which part to make u. And then the other part by default becomes dv. So Lipit stands for logarithm, inverse trig, polynomial, exponential, trigonometric. So when you're looking at your integral, which you will probably have 2 of those types of functions. Whichever type appears higher on the list, you make that part u. And for years and years and years, this term Lipit, which I did not make up, by the way, and I'm going to date myself here, reminds me of the song Whip It. And I have, you know how you have certain things on your sort of to-do list that you never ever get to. Well, one of those things for me is I've always wanted to write a song parody about Whip It and call it Lipit and make it about integration by parts. If you've never heard of that song, it's from the early 80s. The guys in the video wore these kind of funny sort of Lego looking hats. If you'd like to check out the video, I've given you a QR code there. It's quintessential 80s. Anyway, so let's look at some more examples. And for these, I will use Lipit. All right, so I am going to go back to the tablet. All right, so here we have a polynomial and an exponential. Of according to Lipit, the polynomial is higher on the list, so that should be u. So we'll let u equal x squared minus 2x plus 1. And then dv will have to be e to the x dx. Then du will be 2x minus 2 dx. And v, the integral of e to the x dx, will just be e to the x. So, according to integration by parts formula, you'll notice I write it out every single time because I think it's easy to accidentally put the pieces in the wrong places. The integral of x squared minus 2x plus 1 e to the x dx is equal to x squared minus 2x plus 1 e to the x minus integral 2x minus 2 e to the x dx. All right, so now the million-dollar question is, how do I integrate 2x minus 2 times e to the x dx? I mean, I could break that into more than one integral, and one of those parts would be very easy, but I would still be stuck with 2x e to the x. Well, guess what? That is another integration by parts. So here's what I'm going to do. I'm going to put a nice red box around this integral. And then while I'm working on that new integral, I'm going to write everything in red. So using integration by parts again, and again, we have a polynomial and an exponential. We're going to let u equal 2x minus 2. And once again, dv will be e to the x dx. Then du will be 2 dx. And v will be e to the x. All right, now let me just see. Oh, good. Okay. I left another page there. All right, I was thinking ahead. Okay, so let's go to this new page. So we're working on integral 2x minus 2 e to the x dx, which is my integral u dv. So we have uv minus integral v du. Uv is going to be 2x minus 2 times e to the x. And then integral v du is going to be 2 times e to the x dx. And then finally, we end up with an integral that we know how to evaluate. All right, so the value of this, we'll call it the red integral, is 2x minus 2 e to the x minus 2 e to the x plus c. So now I have to go back, because remember, we had our main problem. I really wish I could copy and paste on here. Just put a big box around that whole line and then copy it onto the next page, but I don't know how to do that. So we will just go integral, come on now, x squared minus 2x plus 1 e to the x dx is equal to, this was the original uv. Okay, now I have to be very careful because notice that the red integral was being subtracted, and I now have the value of the red integral. So I have to go minus, great big parentheses, 2x minus 2 e to the x minus 2 e to the x, and then I think I'll put the plus c out here. Okay, so now I think what we can do is combine some terms. I think what I will do is factor e to the x out of that whole big thing. Watch for minus signs. I might do some sneaky things with minus signs here. Okay, so we have one and only one x squared term. Then we have a minus 2x. This is another minus 2x. So that's going to give me a minus 4x. Then we have a plus 1, a plus 2, and another plus 2, because remember, there's a minus out here. So 1 plus 1, 1 plus 2 plus 2 is plus 5. And let's see, make sure I didn't miss anything. Minus 2x. Okay, plus C. All right, the next example. Oh, and by the way, I'm just full of gimmicks this section. For these problems where you have to use integration by parts more than once, they're kind of annoying. I will show you a gimmick for those in just a little bit. A gimmick which, by the way, I don't believe is in your textbook.